All right, y'all. So I'm a little concerned about our fully understanding equivalent resistance and equivalent capacitance for this. Um, or sorry, not equivalent capacitance, equivalent resistance and finding voltage loops and current conservation. It just feels like we don't have the intuitive sort of understanding. And it does take a lot of practice to get a lot of these things down. So I've got three more examples I want to run through. And I think one of the things we're going to try doing is that instead of coming to current conservation and voltage loops when we get to them, we're going to try doing them from the very start, and then we can like use those equations whenever we do it. So I'm still going to make my little chart here, right? And it's going to be a table, I guess. Right, it's going to be 6 rows and still 3 columns, always 3 columns. I use 6 rows a lot because I use 5 resistor circuits a lot, but right, it's always the number of resistors plus 1. And we have 20, 18, 20, 8. That one's also 20. And 10. Okay, so these are our known values. But let's go ahead and figure out our current conservation of voltage loops first. Let's do voltage first. So, right, as we go through, one loop we can go through is this one. Right, so that is 20 equals V1 plus V2 plus V3. And a second option we have is to go like this. And that is 20 equals V1 plus V2 plus V4 plus V5. Okay. All right, so those are our two main voltage loops. Those are two pathways we can go through. Okay, now now we go to current conservation. So thinking about this, right, I usually want to start with the battery. So if I go from the battery, right here is I battery, and it ends up all going into the first resistor. So I battery equals I1. Comes out of 1, goes into 2. So I1 comes out, I2 goes in, they must be equal. We come out of I2, I2 comes out of resistor 2, and then it splits into two pieces. So I2 equals I3 plus I4. And finally, one more piece is that I4 comes out and it goes into resistor 5. So I4 equals I5. Okay, those are your current voltage loop and current conservation equations. All right. So with that done ahead of time, that'll help us a little bit when we get to those stages, but we still actually can't use any of those because right now we don't know any of the values for that. We don't know hardly any of the currents, any of the voltages. So we can't, none of this, right now this is mostly just prepping ourselves for this step. Okay. Yeah. Try and set some of that stuff back in. So where do we start here? All right. Not surprisingly, if I know almost all the resistances, the first place to start is equivalent resistance. Right. So looking at this circuit, I'm going to start with the ones that are definitely in series or parallel with anything else. So I got R3 and R4. They are in series. So R45 equals 20 plus 10. Right? And then this combination is in parallel with this, right? Because current comes out here, comes out of R2, splits, and then comes back together here. So R1 over R345 is equal to 1 over, that's 30, right? 1 over 20 plus 1 over 30. And that's going to give us R345 equals 12. And then, so that's this part right here, about that. And then we know that R1, R2, and this combination are all in series, so R total equals R1 plus R2 plus R3, 4, 5. And that ends up being 50. So equivalent resistance gives us that. Now, as we know, anytime you get two in a row, then you are going to do Ohm's law. So this is going to be V total equals I total times R total, right? Which is going to give us that I total is 0.4. Now we know of current. And that allows us to go back here and be like, oh, I total or I battery is equal to I1 is equal to I2. So now I know this is also 0.4. This is also 0.4. But again, I have two in a row, so I can go over and calculate the voltage. All right, and this is going to be 8, and this is going to be 7.2. Now notice, once I've got those two pieces, V1 and V2, I know I can go over to this voltage loop and be like, hey, V1 plus V2 plus V3 equals 20, which leaves V3 at 4.8. Okay, again, two in a row. Can solve for this. This ends up being 0.24. I have I3. Oh, hey, I3 plus I4 equals I2. I2 is 0.4, so this is 0.16, and I4 equals I5, so 0.16. And we can do the last two steps. This is 1.6, this is 3.2. Okay, so having those equations maybe written out ahead of time may make it easier for us to run, like, once we start going and getting through everything, to run through them. All right, let's go on another example here. So this is one where I haven't given you all the resistances. I guess I should tell you what I'm asking for here. R2 equals question mark. Okay. So again, let's run through all of the equivalent, let's run through all of the current conservation and voltage loops that we can. So again, we start here. What's one pathway? Well, I can go here. Okay. So that's 10 equals V1 plus V4 plus V5. The second loop is go here. This is 10 equals V1 plus V, nope, that's V2 plus V4 plus V5. And these two together tell us that V1 equals V2. The final loop I can do, here we go through R3, skips everything then R5, and I get 10 equals R. V3 plus V5. And now I look at the current conservation. Current comes out of the battery. It can go here, it can go here, or it can go here. So I battery can become I1, I2, or I3. So I battery equals I1 plus I2 plus I3. I1 comes out of this and it goes into I4, and I2 comes out of this and it goes into I4. So what does that tell me? It tells me that I1 plus I2 flows into I4. I3 comes out of here, and I4 comes out of here, and together they're both going to flow into 5. So I3 plus I4 equals I5. And because all that's true, then I5 flows back into the battery, It all said the battery is equal to I5. Okay, let's draw our chart. This is 10. So this is VIR. Total 1, 2, 3, 4, 5. This is 15, 24, 6, 12. Okay. And we know that I3 is 1/6. So, again, anytime we have 2 in a row, we can find the third, right? So V3 is equal to I3 R3. V3 equals 24/6 or 4. Now that's valuable because once we have that 4, right, we happen to know that V3 plus V5 is equal to 10. So I know V5 is 6. Again, can solve for this. I get this is 0.5. I also know now that, wait, hang on. I5 equals I3 plus I4. So that makes this 1/3, which makes this 2. And if I know V4, hang on, where's V4? Ooh, V4 plus V5 plus V2 equals 10. So V2 also has to be 2. And V1 also has to be 2. Now I can find this right here. This is 2/15. And I have I1, and wait, where's I1? I1 plus I2 plus I3, or I1 plus I2 equals I4. I4 is 1/3. 2/15 plus what equals 1/3? It turns out that's 3/15. And 2 divided by 3/15 leads this to be 10. All right. So maybe having these equations out here is going to help you get through that. All right, one more example. It's a little bit different. So this one, what's crazy about this one is that you actually don't want to solve this quite the same way as a single problem. What we have here is we have 2 entirely unrelated loops. You've got this loop, this path, and then you've got this path. And you've got this path. Okay. Those are the 3 paths we have. Notice 2 of those paths share R3 and then R4 and R5, but any electron that goes through R1 or R2, the red path, never goes through any of the resistors of blue or green. What that actually means is we can solve this as if it's 2 different problems. One problem is just R1 and R2. And one problem is R3 and R5, or R3 for R4, R5. So we actually want to set up 2 tables. This table is for, let's call it 1, 2. And we have 1 and we have 2. So the whole voltage is 5. This is 5. This is 10. Because they're in series, equivalent resistance is 15, which makes current 1/3. And, right, if we were looking at the red one here, all of the current that goes into those 2 is 1/3. And then, so let me step back there a second. Let's talk about this. This circuit acts the same way as if we had and then we had a separate circuit, which was like this. They're basically two separate circuits. That's why I'm doing it. Okay. We can call this A and this B. So we'll call this A total. Okay. But remember, all the current coming from the battery here is going through R1 and R2 because they're just in series. So all 1/3. This is 1.67, and this is 3.33. Okay. Now we look at the second one here. A little more complicated, right? We can do our current conservation, or our voltage loop, sorry. And we have our green loop. Those ones tell us that 5 equals V3 plus V4, and 5 equals V3 plus V5. And then current-wise, we have current coming out of the battery, and all the current that comes out of the battery goes into I3. So I battery equals I3. And then it comes out and goes through those two. So that's equal to I4 plus I5. So we make our chart for this one. We have B, all of B, so B total. And we have 3, 4, and 5. This is 10, 30, 20. It's 5. We can combine 4 and 5. They're in parallel. So R4, 5. 1 over R4, 5. 1 over 20. It's 1 over 30. R4, 5 is 12, which means R3, 4, 5 equals 12 plus 10, 22. We can then solve for this value. It is 0.23. Do V equals IR. Already established that I battery equals I3, so this is 0.23. Makes this 2.3. And we said that V5 equals V3 plus V4, so 2.7 and 2.7, leading us to these two final values using V equals IR. They are about 0.09 and 0.14. Now, what if the problem asks you for what is the total current of the battery? The current of the battery overall is actually equal to I of A total plus I of B total. Just so happens that the battery's powering both of these two partial circuits. So we would actually then say that this is 0.56. Okay. All right, hopefully those examples will give you a little more understanding of current conservation, voltage mapping, and how to solve these circuits. Good luck.